Hello, welcome to another coding session. So, maybe a little bit of a recap. We're creating a language here called Bangalang. I just called it that because I thought it sounded funny, but it's a language that is low-level, explicit, procedural, compiled. I feel like those are the main features. We've got a little bit of example code here. Most of it is commented out. Maybe I'll go to the standard library to show some. So we have procedures. The general syntax is like name : type equals something. That's the same for variables too. Name : type equals something. So you can see we have arrays, strings, integers. Yeah, we also have, for loops, ifs, if else, all that kind of good stuff. And we just added structs and type aliases. These are two type aliases. This one as well. And what I'm trying to get to is some sort of nice multi-threading. But the general idea of the multi-threading is that we basically take in an array, then we slice that array up into chunks and send it off to different threads for processing. And I deliberately used the word slice because that's what I want to create now, is a slice type. I think that's kind of what's needed in order to slice up the array. Like in C, you would probably use pointer arithmetic, but I'm not going to implement pointer arithmetic in this language. I'm going to use slices instead. So then we have bounce checking on the slice. It should be very nice. So the idea is that we should be able to have an array, like say 10 I64s, and then we should be able to have like a slice. I'll call it array slice. We don't need to just specify the type. Instead, we should be able to just go like array 0, 1, and that should give us just a slice with one element in it, which is the first element of this array. Or if we were to go like 5, 10, that would give us the second half of the array in this slice. And then in this slice, we could do, we can just index it like we can an array. So it's kind of like a view into a portion of an array. That's what we want to do. So then if I did like array, so the first index of this is 5. So this would be 7, I think. Testing my knowledge here. So hopefully that would exit with the code 6. Yeah, we're starting from index 5. Index 7 has 6, so 5 plus 2 is 7. And that should output the exit code of 6. So let's see if we can implement this. The grammar, there's a couple of places where the grammar needs to change. First off, when we're specifying a type, we can specify a number in brackets, and that makes it an array type. I'm going to put a question mark for the number, because if we just specify brackets with no number in the middle, that means it's a slice. The other place is where we're indexing into something. We can now, whoops, I always do this. I always forget to change my keyboard. We can now optionally, what's going on here? Like this, I think. We can now optionally put a colon followed by another expression. So this part here is going to give us, and we need to be able to do that on the left-hand side as well. Oh, do we need to be able to do that on the left-hand side? I guess so. Yeah, why not? I don't think there's anything bad in it. But when you're specifying a type, you can't do that. So here now, yeah, with the type, we can have like brackets and then optionally a number in the middle. And now when we're indexing, we can optionally have colon and then a second index. You know, that's this colon number here. So let's implement that. I guess the first place, tokenization, no colons on a new token. I don't think we need to do anything there. So parsing, we'll just go straight to parsing. And it looks like we're already in the parsing of a primary. So it's kind of the suffix to the primary. So this is where you have the square brackets, and we would make an index node. So I'm going to change a little bit the types of the nodes. So I was reusing index in types. So if you saw an index node in a type, that would mean that it's an array. But I kind of don't like that. It's not so clear. So instead, what we're going to do is we're going to say, because we know whether we're dealing with types now. So if it's a type, so if we're parsing types, then we're going to give it the type. And then also we'll give it a value. I'm just going to put array here for now. I don't know whether that's the right thing to do. When we're doing an index, there's no value. And actually, I'm going to put this in square brackets. And I want to do the same thing for, because there's the procedure, the special procedure value, data sizes. So yeah, I want to put this in square brackets. Just want to replace that one value. Don't need to do that one. This one's referring to the value. So it's this one. Why is that in two places? Okay. Type value. Yeah, so this one should be. I guess that one should be in brackets. Does that mean that this should be in brackets too? I think so. Let's see. I guess we'll get an error if it's not. So that should be in brackets. That should be in brackets. Just want to be a bit careful that I don't do it in the wrong place. But I think basically all of these. And the reason that I'm doing this, putting it in brackets, is because it's like a special. It's like a special type procedure. It doesn't actually appear anywhere, but previously it was taking up the name procedure, which would mean that if I, in my code here, if I said procedure I64 equals 1, it would be an error because this identifier is already taken, which is like silly, right? Like it shouldn't be, like I haven't defined it anywhere here, so why? So that's why I'm going through and replacing everything by wrapping it in square brackets to make sure that it's not taken. Same with parameters. We can replace all of those. And now we're doing this new one, and we're going to call it, we're going to put array in brackets. So that it doesn't, because you can't have an identifier that starts with a square bracket. So it's like a special one that's not used as an identifier. Okay, now, so we've changed that. The other thing we need to do is say, like, this is actually the start expression node. We can have a start and an end. And the end is optional. So if do we have if peak token type is colon. If we have a colon, then we want to consume that colon and then add a right-hand side expression. Now that's not always valid. So if we are doing it for a type, well, if we're doing it for a type, we can't do any of this. So this is kind of like, you know, if type does not equal type, then we can do this stuff. No, sorry, if it's a type, we can have a single one. That would make it an array. Okay. So I'll put this here. And so this is also optional. Yeah, because if it's a type, this number is optional. And it's a number. We never restricted that. So actually, let me put this up here. I'm gonna, I shouldn't have cut that out. So if it's a type, we're gonna do something totally different, I think. It's gonna be a very special case. And since we're kind of changing everything here, maybe it's also a good idea to no, that's fine like that. So here we're actually going to, I guess we're going to create a number node. If there is a number node to create. So, because it's optional. So if we're parsing a type, we might come across a number token, in which case we create a number node. So the type is number, and the value is the value of this token. We need to do our or return. Like so, we get a number node and we put it in there. So we can do that. And if we do that, that's making it an array. So actually I'm going to put slice here. And then I'm going to say, if we come across a number, now it's an array type that we're talking about. It was a slice, now it's an array because we have a number here. Okay, and otherwise this is for if we're indexing into something. So we create an index node, and then we add start and optionally an end. I think that's all correct. I think that handles all the cases. Let's see what happens. So in type checking, I guess we also want to look at type checking of the index. I'm going to fix this up. So I think we should never go in there. I think what the conclusion I've come to is that types should not go into parse primary. So I think it's good we have that there. So identifier call, here's index. So now we could be talking about a slice. And what do we need to do if we are? So this is if we come across an index node. So we're indexing into something. We might be indexing in with multiple, we might have multiple indexes, in which case we would have 4 children at this point. Well, yeah, because we just added the type node. So the first child would be the thing we're indexing into. The second and third child would be the 2 indexes. And then the fourth child would be the type. So this is saying we're doing a slice. And if that's the case, then the type that we've just applied here is like the element that we're, because normally when you do an index, the resulting type is just an element of the array or whatever it is you're indexing. But in the case where we put two indexes, with the colon, like if we do this, then this is not an element of the array. This is a whole slice. So the resulting type is a slice. A slice of whatever the type is. So what we want to do is create a node where the type is slice. Create a slice type, and then type node children. We're going to add the current type. The current type node as a child of that. And then I think what we're going to do is say that equals the new type node. So that should override the type of this node. So now instead of just being the type of an element that's in the array, it's the type of a slice containing that element. So I think that fixes that up. And we have this type check. So this is type checking the first index. I think we can do that here, and then we'll do another one with the next child, because that'll be the second index, so we'll make sure that's correct. And this stuff here is the compile time indexing. I should say it's the compile time bounds checking of the index, which is not possible for slices. So I'm basically just going to say if we're dealing with a slice, if we're not dealing with a slice, then we can have a go at doing this. But for slices, it's not possible. For slices, we have to do the runtime indexing. The runtime bounds checking, sorry. So I think that's all that's needed. Yeah, so if we're creating a slice, then we set the type to be a slice. We do type checking of the second thing, and we don't do static bounds checking. Okay, that's not so bad. I think generation is going to be the really tricky one. Okay. So yeah, this is it here. I mean, the index generation is already complicated. So let's make this the start expression node. I should have done a copy replace there. Really should have done a copy replace. But I think that's most of them actually. Okay. So this here is not really, so this is kind of like static offsetting. So if the expression is just a number, so like this here, when we're indexing into an array, we just put a hard-coded number here, which means that we can hard-code into the assembly how like the position of this index within this array. That's what this guy here is doing. And I want to keep that. And we could do that with slices as well. The difference with a slice, I'm going to call this maybe the child location, the children location. So if the child is a number, So I guess what we want to make sure that we're just indexing and not doing this. So if the length of the children is 3, because that would be the thing that's being indexed into the the thing that's being indexed into the expression node, this one, and then the type. So that would mean that we're not doing a slice. Well, actually, I guess we could know that because at this point we could know that because the do we have the type node? Yeah. Because the type node does not equal slice. So we're not doing a slice. We're not creating a slice. And we have just a number as the index. So, and this is the case if so this is the start expression node. So here we're getting that number. That makes sense. And offsetting the child location. But what if the child, I guess we want to get the child type node. Get type of this guy. So if the child type node is slice, then we need to do something special, right? It's kind of like the child or the data location equals the child location. But if we, and then it's just like, then we use this. Yeah, I think this is right. I think this is right. Yeah, this makes sense now. Okay. So if we're not dealing with a slice, then yeah, we just get this location and we add an offset to it. But if we are dealing with a slice, then the location of the data is actually well, a slice will be composed of a pointer to the data and the length of the data. So the pointer to the data is the start of the slice. So isn't that exactly the same? What's the difference here? What am I trying to get at? I had in my head that it should be different. I think it's because yeah, because normally if it's an array, then this location will be the start of the actual data in the array, right? It's just right there. But with a slice, the first thing in the slice is a pointer to the data. So we need to dereference that, which I guess is like doing this. This is a dereference. Okay. So I guess we take the data location. So this is the location of the slice, and we're like dereferencing it. We put it into a register, if we use register num, is that okay? I don't. Maybe it is. It's going to override this, but if we don't use that anywhere else, then that's okay. I think. So can we just do this? Like we move it to a register and then we treat it like a memory address. And then we offset it. Yeah. So this is the start of the slice, and then this basically treats it as a pointer like it is, so it goes to where it's pointing to, I believe. Let's see if this works. I'm curious. And then, yeah, so that's our kind of shortcut. Now we get more stuff about the start expression. Oh, we did child type node here. We don't need that there anymore. Then we do bounds checking. Optional bounds checking of that stuff. And this is like offsetting the address by the correct amount. And then returning the memory. Okay, so I'm going to say in here that if we're dealing with a slice, if we're creating a slice, we need to do something different. We need to allocate some space for it. Size. And then I think we pass in the context again. Yeah, like that. So that should allocate some space for it. And then we need to do like a couple of moves. A couple of copies really. So maybe we should call copy actually. That would make sense. What does copy take? Source and destination locations. Type node context. So the first thing we want to copy in is the address, right? The address that is the start of the yeah, that is the start, which should be now this address location. So that's the source, and the destination, since we just allocated, and the pointer is at the start of the object, should be IRSP0, so it's at the top of the stack. And then IRSP address size, that's where we want to put the length location. So the length of a slice, that's interesting. How do we get the length of a slice? I guess we need to evaluate the start and the end. Length location, and we want the length before we come into here, right? So I guess we want to bring this out. Actually, it's we need to do a find for this and check this, because yeah, stuff like this. Because types don't use index anymore, so if it's a type and the value equals array, then we multiply it by that size. If it's a type and it's a slice, then we can return address plus 8, I think, because that's the size of a slice. Let's go back to type checking and also see where we use index. Yeah, so this is trying to say it's an array. We also need to say it could be a slice. So if it's a type and the value is, damn it, value is array, or the value is slice, we go like that. So that should cover all those cases. What do we got down here? That's basically the same check. So let's copy that behemoth of a condition. Put that there. What do we got here? Case index. So this is parsing a primary, so that's fine. That should stay like that. But I've used the wrong, is it the child type node? So that index is fine. So actually, I think, I'm just thinking, for this condition, do we really need to check that as type? We already know we're dealing with a type node, so I think it's safe just to say like, that is that, or that is that. I think that's safe. Because now the only kind of nodes that can be in a type are like type nodes and reference nodes. And reference nodes don't have values, and these are special values for type nodes. So I think that's all good. Why is it not happy? Because of this bracket. So we can just take that out. That's a bit simpler. I like simpler. Oh yeah, so I need to put this here. This, we also know this is a type node. So if we're dealing with an array or a slice, let me do that. Yep, that sounds right. Where's another index? So this was trying to say if it's an array. Oops, I got rid of the quotes. What else we got here? So for the type name, yeah, so I think probably I can just do this, right? I think that's fine. So for the type name, if it's this is saying if it's an array, then we put brackets with a number in. If it's a slice, we just put brackets. Okay, we get in there, get in there. This is the same condition as like up here. Well, I don't think we need that condition anymore, actually, for this one. because everything's a type node except for the reference node. Okay. Get type value. So this one gets a bit interesting. So yes, if we find a reference, then we recurse. That's true. And I think I might start putting some asserts at the top of these. So let's say, because here, these ones, we're kind of assuming that this is a type node. So we should only come across these. And if we don't come across those, something is wrong. So get type is type. They should not be like that, but like type result. I guess I'll put it after the null. Okay, and upgrade types, resolve types as struct member. Yeah, so I think it's just those ones I wanted to, or type name also. Let's make sure that that's correct. Okay, I think that's enough. That's enough for now. So get type value, that's right, I was looking at this one. So we know it's a reference or a type. If it's a reference, we recurse. So actually, basically, now that we know it's a reference or a type, we know it's valid. Really, I want to go down to the bottom node and get the value from it. Because now it could be like a type node, which is array, which nested inside it has a type node, which is like I64. And really what I'm saying with this is I want to get the I64, the deepest one. So I think it's just a case of if the type node has children, go to the type node. Otherwise, give me the value. That's basically it. Okay, I think we've corrected all that stuff now. So we can go back up here to this craziness. That's right, we were trying to figure out the length location. So I think I'm going to say the length location by default is an immediate 1. And then if we're talking about an array, we're going to override that with an immediate, which is, well, for an immediate, we don't actually need to convert it to a number. We can just go like this. Yeah. So now it's going to be the offset into the array. No, the length of the array. That's good. Otherwise, if we're talking about a slice, then the question is, what do we want to do? So if we're talking about a slice, then it's the child location. So this is the location of the child slice. But then we want to offset past the pointer, because remember a slice is a pointer and then a length. So if we offset past the pointer, we get to the length. So that's the length location. Okay, I think that's good. I think that's good. And then we can just put that there. And we can use it here. Great. I'm pretty happy with that. And because we're doing an allocation here, we need to, I think it's down the bottom somewhere. Contains allocations. So at the moment, if it's got a call in it, it contains an allocation. But I think we also want to say if, so this is just recursing, yeah. So if we find a node which is I was just going to say if we find a slice node, but a slice node, it could be referring to, you know, something we're just accessing, not something we're creating. So maybe if we find an index node, where were we? If we find an index node, with 4 children, I think that means that we're slicing. Yeah, pretty sure that means that we're slicing. Or, yeah, maybe it's actually clearer to be like, you know, if the type of that node is slice. Let's try that. We might have to do get type value here. I don't think so though. Let's see. So now we know that that contains allocations. That's used in the call, like here. And we want to use it also here, but I don't think we need this. We know that we've just allocated on the top of the stack. So that'll either just return saying it's on the top of the stack, or if, well, there's always going to be allocations though, isn't there? Because the existence of this has said that there's going to be allocations, so it's going to return this. And isn't that also the case for the, where is it, for the call? Oh yeah, the call just does it regardless. The call does it regardless. And this does it. Right. Yeah, this does it if there are allocations, because this is just accessing existing memory, existing variables. So, and the reason for like not just returning relative to the stack and returning a copy of that address is because then if we do allocations, that changes this pointer and means that if we do relative addressing to that pointer, it's going to be broken. But yeah, I kind of just realized that here it's like we're always just going to do this. Okay. So what else do we need to do in here? I want to do some extra checks. So because we have a second index, right? We also need to set this. What are we copying? Because that's the length location of the child. So this is not the right thing. It needs to be the length of our slice. So we need to figure that out. So let's first do some checks. So the end expression, well, I guess we're going to need to get the end expression. Like so. End expression node. End expression type node. End expression location. And I guess we probably want to do +2 so it doesn't mess with the start expression. Okay, and we need to get the next child for it. So that's our end expression. Again, we need to compare it to the length, make sure it's not past that, and compare it to 0, make sure it's not lower than that. And then we kind of want to do a comparison between the start and the end. Need a comparison between the start and the end, and we need to figure out the length. Well, I guess to do this comparison, we need to figure out the length. And if the length is negative, that's when this should panic. Okay. So how are we going to get the length? It's basically start minus end, right? I think the problem is, though, that this start has been multiplied by the element size. And that's going to cause issues. So we kind of need, I guess we can use +2 here. This is just a temporary thing. So this is kind of like the offset location. And we're going to need to do a move. So, I mean, I guess a copy. We're going to need to copy into the offset location from the start expression location. And I think we need to be a bit careful about these types, because this is the type of the index, right? So actually it should be I64, and that should be I64, and this one should be a reference. Yeah, I think that's better. So we're copying from the start expression location to an offset location, and then we're going to use this offset location, we multiply that by the element size, and add that to the offset to get the new address. Yeah, we don't want to modify this guy. Yeah, so we haven't modified that guy, so that's good, because then down in here it's going to work properly. So we have the start and the end. So now we want the length. Slice length, so we need to store that somewhere. Can we just store that in one of these, the start and the end, or do we need them? I mean, I think all we need to do is like find out what the length is. So let's do like a sub if we subtract end, if we subtract start from end, now that is going to be the length. We compare the length to 0, and if it's less, that's bad. Yeah. Kind of sucks that we're reusing that name, because now that's not what it is anymore. But I kind of don't want to use even another register. And now that we've got that, this is what we want to copy into as the length. Yeah, that's right. That's what we want to copy as the length. Why is it not happy about that? Ah, it's the gen. We're in generation, so we can't do that. Copy the start expression location to the offset location. And we need the type node. Ah, that's a bit tricky. Maybe just to get around it, I'm just going to do what I was initially going to do. I'm just going to do like a copy, so I don't have to worry about this size business. Because I know we're talking about registers here. So I should be able to just do that. Move the start expression into offset. Okay. And then down here, we should be able to just do a move from end expression to here, this memory. Maybe I'll give that a name, you know. So we could say this is the slice length location. You know what, maybe it's best to, maybe it's best to do that move first, actually. Maybe that's clearer. So we move the end expression into the length. Then we subtract the start expression from it, and then we compare it to 0. Yeah, I think that's better. That's better. Okay, good. And 0 is the slice address location. All right. Okay. I think I'm happy with this. I think, I mean, confidence is not particularly high, I have to say, but let's see what happens. Index to out of bounds of array slice. So array slice should have a length of 5. Also, array slice is a slice, so this here is compile time bounds checking, which is what I said we should not be doing. So let's go back to type checking where we do that and see what's going on. This is it here. So actually this is saying that we're creating a slice at this point, but it should be, I think it should be this one. What we're creating a slice of should not be a slice. or what we're indexing into should not be a slice if we're going to do bounds checking. That sounds right. That sounds right to me. Okay, failed to type check. Okay. So we're going in here, which is wrong. Let's have a look. So we have an index node whose child is F32. Yeah, I think let's go to parsing. I think this might be to do with this .index stuff. Oh no, there's nowhere that we do dot index here, except for right here. But the thing is, this is like, if we're particularly parsing a type, or if we're particularly doing like a type primary, but other kinds of primaries can include types, like a left-hand side primary, or yeah, left-hand side expression, which is going to say, hey, I'm doing left-hand side stuff, can include a type. But then that should be, like when I do, if I do parse left-hand side expression, if I find left-hand side expression, yeah, we use dot type when we go into that primary. So it should be correct, right? Then it should use dot type, should create the correct node. Is there any case where it would not? Type primary. Well, I guess actually like this is getting parsed as a right-hand side primary. So it's not going to say that's a type. And actually this is F32 index. This is probably this line. Let's have a look. I'm curious. Yeah, it is. Okay, and because it's in the right-hand side, it doesn't know it's a type, then the parsing doesn't take care of this. I think one place we could take care of it is this resolve types. So in here, I guess when we get to the identifier and replace it, it's going to replace like the F32 part. Like it'll get this identifier and say, okay, this is a type now. But then when we go back up the tree and get to the array part, we need to say, this is not an index, this is an array actually. So I'm going to make this return a bool. I'm going to return true here and false here. And then if this returns true, it means we just replaced a type. And then I'm going to say, if we come across an index, if we are an index and we just replaced a type, then we want to change to be a type. And if so at this stage, so I'm just trying to think, how can we tell whether it's a slice or an array? So when we're parsing a type, so if it's an array, it'll have a child, a number child. So if there's no children, no, it'll have one child if it's a slice, because that child is, the one we just went to, the F32. So if it's an array like this, it'll have one child, which is F32, one child is 3. If it's a slice, it'll just have a child, which is that. That's how we can tell. So if it has one child, it's a slice. I think we can just do a one-liner. So let's go do a ternary. Like so. So that should hopefully fix up the node. Okay, operation size not specified. At line 33. That's this comparing, so we're comparing a memory address with 0 right before panic out of bounds, which actually reminds me, I wanted to say panic negative slice length. Let's add another panic here. I guess if we end up adding more panics, we can extract this into a procedure and then just like call it to generate the different things. Okay, and then we're going to make a message, so we'll put that in here. This should be defined bytes. And actually, while I'm at it, I want to put a new line on the end. Panic negative slice length, which is 28 characters, plus the new line is 29. So that should be 29, and we add 1 to that because we put the new line on the end. Okay, let's run that again. Yeah, so now we see this one, and so the compare is just before that. So it's this compare, yeah, because that's going to be a memory address. And I think we know that it's a 64-bit, 8-byte, you know, it's an I64, the length. So I think we could just hard code that in there. Panic index out of bounds. So if I take out that new code, is it still panic? No. What about now? Okay, so that array indexing worked fine. What about creating the slice? Okay, index out of bounds. That's true. No, well, this should be fine, actually. So maybe yeah, because when we're specifying the end, it's actually like 1 past the end. So this would give us from index 5, or is that right? Usually with these kind of things, like this is inclusive and this is not. So if I go 10 minus 5, it should grab 5, it should have a length of 5 beginning at index 5, which would mean indexes 5, 6, 7, 8, 9. Yeah, so I think this should be valid. So I think it's probably just that we need to change our check. This out of bounds, it should be JG. Okay, now it's happy. And if we index with slice 2, do we get 7? No, we get 0. Okay, so let's have a look at the assembly. Something's gone wrong. So here we're allocating 80 bytes. Yep, 10 8-byte values is 80 bytes. Initializing it all to 0. Very nice. Here we are assigning, right? It's just an assignment. But for some reason we're allocating, which is bad. So let's have a look at the assignment. Here's the allocation. Why would that be allocating? So that should allocate, yes. This is an index node, an index of array. So this index well, I guess we can't get at the type node very easily. Oh no, there's the left-hand side type node. So it's an I64. Really? It's an I64, but if I go to left-hand side node, it says it's an index. Oh yeah, so that makes sense. Yeah, actually that makes sense. Okay, but what was I actually trying to get at? Is struct member I think that looks good. So should there be like an extra condition? I think normally I put that first. But I think that's the issue, right? That it's a struct member. But because this is an index node, no, we're not assigning to a struct member, but we're assigning to an existing thing. So maybe we should just say it needs to be an identifier. Yeah, because we have an index node, this is gonna, of course it's not going to be in there because we're just looking at an index node. And when we're doing initial assignments, it can't be, it needs to be just a plain identifier. So I think that should work. Yeah, that got rid of our allocation. I don't think that was particularly causing problems. It's just it shouldn't be doing it. Okay, now this is the this is a beast that we have to look at. So we allocate some space. We copy 5 into R13 because we're copy 5 into 13 and we compare it to 10. Make sure it's not above or equal to that. Then we compare it to 0, make sure it's not less than 0. Then we reference RSP plus 16, which is the address of this array. Yeah. And we move this index into R14. Multiply it by the element size. That's not the element size. Element size should be 8. So why is it saying 16? Let's go to generation. Multiply by element size. Byte size of type node. Yeah, the type node is a slice. So actually it's byte size of I guess you could say it's not the child type, but this type node, I guess we could say it's the child of that, because it would be a slice of something, right? I think we could do that. Was that bad? Apparently that was bad. Okay, what does this type node say? Type node is I8? Really? Because we're not saying that we have to be in the slice business for this. Okay. Well, yeah, so that's what we were before. So we need to get the size. Where is it up here? We need to get the size of an element. So whatever we're indexing into, whatever we're indexing into, we need to get the size of it. That's a bit of a pain. Okay, let's try it anyway. I mean, we have to. So, element type node. So if the child type node is an array or a slice, because the way in this language I've kind of, maybe I shouldn't because it's kind of weird and not really necessary, but I've kind of made it so that you can just you can index anything. It's just that if you're indexing something that's not an array and not a slice, you can only do index 0, right? Otherwise, it doesn't work. So if it's either of those, then we get the first child. And then that should be, what it contains. Otherwise, we just get the type itself. I think that should be the element type node. Let's try that. Okay, we got 6 back. So now, now we got the correct info. And yeah, 6. That's what I said it should be. Okay, that's really cool. So if I try to index 12, it should get, oh, we should have got an out of bounds error because it should know that that's out of bounds. That's the second one. We should see it 12, right? Because it's a hard-coded 12, so we should see it 12. That's allocating 12. Huh. I was sure that that 12 should appear in the, so where should it appear? On the 4th line, we're indexing using 12. So 1, 2, 3. Something else that I kind of realized I think is still not happening is, or maybe it is. No, we need to add here. Expression. Because I like to have a comment for every, so assignment, expression. So this is it here. Why is it so short? That's the 4th. That's it? Allocate, copy stack address. Do some copies with call exit. So it's grabbing the stack address. I feel like it's not doing everything that it should be doing. So we're doing it an index. Because it should be, this should be compile time. No, because it's a slice, it can't do compile time. So it should be triggering this one. And I just realized this is going to appear even in cases where it doesn't need to. because it's a hard-coded offset, we just do this. Which means that we skip the bounds checking. So maybe we should do all the bounds checking and stuff, and then we should skip out. So we do all the bounds checking, then we check for this special condition and skip out. Like we don't need to do all this stuff, right? Panic index out of bounds. Okay, great. So now if I go back to, was it 7? No, 2. Yeah, okay, awesome, nice. What else can we do? We can say like, we can put, so that should be 6, should start from 6. So then we should just go 1, and we should get Xcode 6. Very nice. Okay, we're in hour 16. I think I'm going to leave it there. Like one other feature I'd like to put in is like something like this. So if you omit it, then it would just assume you want to go all the way to the end. Or you could do like this, and it should assume you want to start from the start. But I don't think we need that right now. I think it's cool that we have slices working. Yeah, I'm sure there's bugs. I'm sure there's bugs on so many features of my language. I really need to have another go at testing, doing a good job of it, a better job of it. But now we have slices, and I think that's really going to help with our multi-threading. I think the other thing we're going to need is some kind of like some multi-threading primitives, I guess you could say, like some atomic integers, which means that, you know, when you add to the value, for example, add to an integer, you can be guaranteed that it's not going to, that it's going to happen atomically, like it's not going to be interfered with by other threads. And mutexes and stuff like that, we might need to sort of spend a session just introducing those kind of primitives, semaphores. And then the next session, we should be able to create our like thread pool and our way of slicing up the workload and spreading it across threads. Cool, I'm glad we're finally getting to this. But it's kind of nice that we've added some really nice features along the way, even though it kind of feels like a detour, but I don't know. I'm pretty happy with these. I'm pretty happy that we've got slices now. I think that's good. That could potentially simplify a lot of our code. Instead of using these boundless pointers, we should be able to use slices. Oh, that reminds me. Sorry, I keep going on tangents, but we should be able to do something like this. We should be able to implement something like this so that we can get the length of the slice. That's a handy thing to know. And maybe even a dot raw. And we could probably implement it for arrays as well. And the dot raw would just give you a boundless pointer, right? So then you can do whatever you want. I wouldn't recommend using it, but it's there if you need it. Or if you just don't want bounds checking, maybe you can use the dot raw. Okay. Yeah, if you're in like a hot loop, maybe you want to really optimize and you don't want the bounds checking. Anyway, that's enough for today. Thanks for stopping by. Have a good one. Ciao for now.